Friends, it's a great pleasure to welcome Professor Samir Mathur once again to IUCAA. It has been a rather longer interval of absence for him. Samir followed a fairly canonical path which many of the distinguished theoretical physicists have followed. IIT Kanpur and Masters, and then PIFR PhD. Had a first postdoc also in PIFR and Harvard, MIT, and finally settled down to Ohio State University. That's where he is the professor of physics for the past several years. And on a personal note, I must tell you that I had known his wife before him. I have offered her a PhD position, but she didn't take. And so it doesn't end there. About 15 years or over, around a dozen years back, we thought that we should get both of them together. We offered both of them a position at IUCAA. That also they didn't take. But we don't let them simply, so time to time we keep on fighting. And he's going to talk on one of the most debated topic over a quarter of a century. And nobody yet knows what we understand or not. I must tell you that there was a very celebrated bet taken by two very distinguished guys, Steve Hawking and Kip Thorne. And that was also, in a very dramatic way, settled in that GR meeting in Dublin, which I happened to attend, where Steve Hawking conceding to Kip Thorne, and the bet prize was a year subscription to one of the very interesting magazines. I won't name the magazine. So with that, Samir, it's all yours.
Okay, it's a great pleasure to be here, and thank you very much for that kind introduction. So I'd like to share with you my thoughts about this very now ancient problem. So this is the stuff for which Stephen Hawking became famous, and I will just assume that you don't know anything about it other than the fact that Stephen Hawking proposed this paradox. So we'll start from scratch, and then we want to just understand what the puzzle is and what we now think in string theory the answer is. It would work best if you keep stopping me and asking questions, more like a usual seminar than a colloquium, because the topic does sound more confusing than it ought to be. And if you stop me with questions, it will actually help everybody understand what's going on, and it will also prevent you from falling asleep. So, yeah, please do keep stopping me whenever anything is not clear, and I'll manage to cover what I want to say. So, you have time to ask whenever you want. Okay, so let's begin with looking at what is the information paradox. And it really all starts with the very basic fact that gravity is an attractive force. So if you take some mass here, which I have called capital M, and you take a test mass here, little m, and you put them at a separation r, then if you just look at Newtonian physics, the potential energy is minus gmm over r, and this minus sign is what tells you that gravity is an attractive force. Now this little mass by itself, as Einstein taught us, has an intrinsic energy mc squared. But when I place it near this heavier mass, there's this negative gravitational potential. So if you just want to be schematic and rough for a first pass, I can say the total energy of little m is mc squared, and then I add in the PE, so I get minus G and then over R. Now this thing is a little funny if you look at it, because if I keep making R smaller, at some place this number becomes 0, and for even smaller R it becomes negative, and you can see that E becomes negative if R is less than Gm over C squared. So what does that mean? Firstly, because I'm talking of mc square, I'm talking of relativity, special relativity. And because I'm talking of gravitational potential, I'm also talking about gravity. As we know, when you want to talk about relativity and gravity at the same time, you should properly work with GR, general relativity. So if you do the same thing with GR, it doesn't change much. You only get an extra factor of 2. We had Gm by C square on the previous slide, but now you just get 2Gm by C square, and the fact remains true. If you have a point mass m here, if you come within a radius 2Gm by C square, in there, you can actually have a particle whose net energy is negative. This radius is called the horizon radius. We'll come to that issue later. But now this already looks a little funny, because energy is conserved. This same object, capital M, has the same energy as n, but plus a pair of particles. This one has negative energy, this is outside, so maybe it has positive energy. You can make the total energy 0. And so it looks like you can just create particles from nothing. They totally overall doesn't cost anything. And so you can extract as much energy as you want. And the only catch to this might be that this M has to be compressed to a sufficiently tiny dot so that it can get close enough for this thing to work. If this thing was very fluffy like a big ball, then if you go inside a ball, it's not the same Gmm over R potential. So the question is, but as long as you can compress this to a small enough dot, you have this magic that you can get particles for free, because the gravitational negative potential can overrun the intrinsic energy mc squared for anything, and then you can get particles for free. So can you compress M to a sufficiently small dot? And that's where black holes get it, because if you look at the picture in general relativity for a black hole, if here is a star which has finished its burning, then it can start to collapse. And if I draw time up there, the angular circle like this, and the radial direction outwards, the star starts shrinking. But if you look at what the metric is doing, here I've drawn the light cones, and far away the light cones do their normal stuff. You can go in or you can go out by following the light cone. But once you come close enough to the place which we call the horizon radius, that's the radius we had on the slide. If the light cone points purely inwards, you can go in, but if you try to fly out, you can at best stay at the same radius, you can't actually get out. If you go further in, you can see the light cone points purely in, so you can go in slower or faster, but you can't even stay at the same radius. So everything has to keep crashing down to a point, and so everything inside this horizon has to keep squeezing and squeezing till it all reaches one dot. So gravity does this for us automatically. It squeezes things down to a dot, and then we have all the conditions we required on the previous slide. Now if you come close within this horizon radius, anywhere inside this radius, you will find that you can have this magic of net negative energy. So it's all very simple, all very robust. This is all that you need to know to understand where the paradox comes from. You won't always draw this complicated picture. We just draw this central singularity as a dot, and this we'll just call the horizon, and this will be our cartoon picture of the black. Okay, so let's see what this means. Nothing much happens by itself, but once you bring in quantum mechanics, so that's the comment I had here. In classical mechanics, all this is true, and you might think that you can mine the energy of the black hole by putting a particle in here, but the question, how are you going to do that? You aren't going to reach into the black hole and put a particle there. So while it may look possible that you can create a pair of particles from nothing because of the energy balance, how are you actually going to go to the black hole and do that? But it turns out that it happens by itself. So in quantum mechanics, the vacuum is not really empty. For example, if you take this room and remove all the air from it, you might think it is empty, but you still have quantum fluctuations going on. So every once in a while, electron-positron pair will pop out of the vacuum, and then it will disappear back again. The cost of the pair will be mc square plus mc square, that's the energy delta E 2mc square of the fluctuation. But as long as the fluctuation lasts for a short enough time, so delta E, delta T is less than order h bar, the fluctuation can exist. So we all know these quantum fluctuations exist. They are observed in things like the lamp shift. They are part of what we see in the Schwinger effect. So we know that quantum vacuum behaves like this. But let's see what happens if this fluctuation occurs near the black hole horizon. So now suppose the same fluctuation is happening here. Then this particle has net negative energy. This has net positive energy. And the total delta E now can actually be 0. And now you can see that delta T Doesn't have to be any finite number, it can be all the way to infinity. In another language, what you can say is this particular fluctuation is on shell. This mass m plus 2 particles has the same mass as m itself. So this is just an allowed fluctuation. The wave function can just flow into a situation where this pair is produced, and in fact it will do that. And so now you will have these particles, they won't go away, they will always be there. The outer member of this pair cannot just drift away, and that is what is called Hawking radiation. The inside member will already have negative energy, it falls in. But because it has negative energy, you can see the energy balance works beautifully. The energy comes out at infinity, that's normal energy of a normal particle. This guy has reduced the energy of what was in here, so the black hole has gotten less energy, and the hole is now evaporating. Question.
So, aren't you assuming that the pair is produced at different location?
So these two locations that you have here, indeed. So what actually happens when you go to the detailed calculation that Hawking did, what you will find is that you actually have to consider a wave mode, which is never a point-like object. The wave mode actually straddles the horizon. It starts from one side and goes to the other side. The wave modes that actually straddle the horizon, as they evolve, those wave modes are stretching. And when they stretch, you actually get a pair creation. This part of the wave mode deforms to create a particle inside, and this part of the wave mode deforms to create a particle outside. So the usual colloquial ways of saying that both the particles are created at one point outside and then one falls in, I don't know why Hawking himself said that in many colloquial ways. It's not accurate. If you actually see the modes which straddle the horizon, their separation at the horizon is what causes the effect. It's a quantum effect, so you have to think of the wave function, and that wave function has to have parts on both sides. And that's the part which stretches. So let's see.
Samir, you can still have a pair created outside the horizon, just outside. And since it's supposed to, it has positive delta E, so it can have a short delta E.
Yes.
But that could be short enough for one of them to go in.
Yes, it can go in.
So you can have that process also.
You can, but it doesn't do you much good. And the reason is the particle which is formed outside and then goes in actually doesn't have negative energy.
Once it goes in,
it still doesn't. And it's very interesting because I cheated a little bit. I mentioned the intrinsic energy mc square. I mentioned the gravitational PE minus GMM over R. I never mentioned the KE. And so if you throw something from outside, the energy is conserved along the track. If it was made outside, it has positive energy, maybe it was at rest. As it falls in, it picks up a KE, but the net energy remains positive. So that's not the kind of fluctuation which will help you. And as I was saying before, we don't know how to do this with a black hole because who will go in and if you're not doing put the particle inside by throwing it from outside, for this reason it doesn't work.
No, but the other particle remains outside.
But the total energy is still positive, so the fluctuation can't be on share.
So then what happens?
The fluctuation just goes away, just like in this room. The pair comes for a while, the other particle can't receive very far because the overall wave function can't sustain that. So it just phase mixes with the next phase and the phases cancel after a while and just goes away. But this is very crucial that you can't actually create these particles inside the negative energy thing by throwing them from outside because then the kinetic energy always comes and the net energy is positive. But quantum mechanics has been very nice to us. It automatically creates it at zero velocity inside. And now there's no kinetic. The potential is more than the rest mass mc square, and you actually have it. So you need the quantum mechanics to do this. So with the hand up somewhere, yes, please.
So, since we are dealing with relativity, what would be the time? Is it the co-moving time or what time?
Okay, so this is of course a bad picture. If you actually draw the nice slicing of the geometry in curved space, so you do all nice global slices through the Penrose diagram, it turns out the length scale involved in the process, there's only one length scale which comes into everything. And the length scale is the Schwarzschild radius. So if you take a solar mass black hole, it's 3 kilometers. So roughly speaking, what's going to happen is the particles which are produced, I said electrons and positons just for colloquial purposes. They're usually very massless particles like gravitons or photons. The wavelength will typically be ordered the Schwarzschild radius. The rate of production is such that when one particle is produced, it takes the time of the order of the crossing time across 3 kilometers to leave, and then the next one is produced. Okay, so you know there's only one scale in the problems. Everything comes from there. And so if you want to know after how much time the black hole evaporates, you know the energy of each guy because I just told you the wavelength. I told the time of production between successive particles, just the crossing time across 3 kilometers. You can figure out how long the black hole takes to evaporate. There are no other numbers in the problem, so it's very simple and good.
I'm asking about the delta T, the time it takes to, there is an upper cap within which the particle should annihilate, right? So, in quantum mechanics, we just take the classical notion of time. But
yeah, so what will happen is because I said the wavelength is 3 kilometers, then the annihilation time for those particles is also 3 kilometers worth of time. There's only one scale in the problem. So you have to see how a master's particle will fluctuate and then reannihilate. It's the same energy scale. So in the good slices of the black hole, which you're not seeing here, every scale will be 3 kilometers, energy time is also 3 kilometers, and that much time it will separate by 3 kilometers and come out. There's only one band scale, and that's all that happens. Okay, so we have this Hawking radiation here, and then this is the thing that Hawking told us. The outer particle, as we said, drifts out as Hawking radiation. The mass of the black hole a little less because this had M and this was net negative, so I've drawn the horizon radius, which is 2 gm by c squared, is a little small enough because the net mass inside is less. Then the process can happen again. This time maybe the positron stays inside, the electron goes out, but the process repeats, and this thing radiation keeps coming out, and in the end, the black hole just becomes either completely goes away, or this goes down to a Planck size, and after Planck size, you can say, I don't know what happens, so maybe it stops. But in any case, pretty much all the black hole is gone, and the hole is evaporating away. That is Hawking discovery of 1974, and he was very happy with it, so you can see him smiling.
Yeah. It says a particle production. So suppose that we electron, so suppose how there is no preference.
If there is no what?
The between electron and position, which one goes up?
So right now there's no preference.
No preference.
No. But if the black hole had a charge, sometimes black holes also have a charge. If the black hole had positive charge, then the positive has a preference to get out because it's repelled.
Hence there is.
In the neutral black hole, there is no preference. No. And actually, I will come to that in a second. Yes, please. Back there.
What is the initial kinetic energy of this particle spread outside to move away to?
Right. So the kinetic energy is very small. So if the particle has wavelength of 3 kilometers, it's basically going to have energy only of that order. So when I said it's created at rest, it's a quantum, right? So quantum will never really at rest. The master is quantum. It's basically just a dispersive wave function. If you make a Gaussian wave packet of wavelength 3 kilometers, it just drifts. What happens most of the time is that guy actually falls in. Once the wave function is there, it can go inside also, right? So gravity is inside. That's why the leakage rate is very small. It's a very slow process. And there are lots of quantum fluctuation, but most of them actually end up falling back in. But it's just spreading and so on, and just once in a while the guy leaks. But most of them do fall in because it's a wave function, natural dispersion in that gravitational field, and it just leaks out once in a while. There was another question there.
Yeah, so this process, it seems like black hole will be finally fragmented.
So how do you mean fragmented?
Like there are many particles will be created, and then probably some of them will come together inside the horizon, and then that's what I think like fragmented.
So it's not fragmented, they're all inside the horizon, so maybe they're densely packed in there. Would you call that fragmentation? That's what's all in there.
Density
It's all in there, and then we can talk about what's in there. But they're all like in a very small region, because this radius is actually shrinking, so it's all like getting compacted sort of.
I have a question.
Yes.
Is there a preference on the species of particles? So you said you give electron positron as an example, but could it also be just 2 photons for the photons?
Yeah, so most often it is photons. So that was one of the discoveries of Hawking, that the radiation was purely thermal because gravity couples universally to everything. So the suppression is only by the energy. So it's a thermal thing in the sense that the probability of everything is just equipartition just by the energy. So probability of emitting something of mass m is equal to minus m over kT. So the temperature to this emission, the thermal emission, and then like in startling, the probability of any state depends only on the energy. So the massless particles will most preferentially emitted. So if a black hole radius 3 kilometers, they emit particles of wavelength 3 kilometers. Yeah.
And among massless particles,
no preference. So they cannot be. So that's the important part of the theorem. It's coming out of gravity. And because coming out of gravity, it has to be universal, otherwise it wouldn't be called thermal. So the thermality was an important part of what Hawking noticed. So it's completely universal. 2 massless particles will have the same amount of radiation per spin degree of freedom. Yeah.
delta E equal to 0
I couldn't hear that.
why was delta E equal to 0 in this scenario?
So delta E equal to 0 was because the particle inside had negative energy and the outside had positive energy. Is this what you're asking?
Correct.
Yeah, so I just chose that as an example. We can also have fluctuation with delta E not equal to 0, but they will soon cancel away. Just like in normal energy conservation in quantum mechanics, you have to sum over all phases over time. Although the delta E is not 0, they just fluctuate, the exponential just cancel away after a while. Only the one with delta E equals 0 survive. So I just wrote those in. Okay, so let me go on with this. This is Hawking's discovery. And at first, everybody was very happy, and Hawking was particularly happy because a couple of years earlier, Bekenstein had produced something which was sort of going in the same direction. Suppose you take a black hole and you take a box of some gas. It has some entropy, which I've called S of this matter, the entropy of this matter, and you throw it into the black hole. Then the gas goes to the center and it disappears. And then you might ask, have I reduced the entropy of the universe because the gas is now gone? Now you don't want that to happen because second law says the entropy never goes down. So how should we deal with that? Well, of course, Bekenstein knew that the hole will get bigger. If it eats something, the hole gets bigger. And then with some work, we figured out that if you attribute some entropy to the hole, which is proportional to the area of the hole, then somehow everything works out properly. Whatever entropy you lose from throwing the matter in, if you add to it the entropy which you gain because the area actually increases, the net actually always stays the same or increases. So you can save the second law of thermodynamics if you attribute an entropy to the black hole, which is actually proportional to its area. Bekenstein did not know the coefficient, but he got all the rest of it. Its area in units of Np squared. And so this suggests that black holes have an entropy and even suggests almost up to a factor which he didn't know what the entropy of the black hole should be. If that were true, then using statistical physics, it means the black hole has e to the entropy states. And for solar mass black hole that is this many states, that number doesn't mean much by itself. But we just note that if you actually compute the entropy of normal matter, like the gas making up the sun, that is much, much smaller. So whatever entropy this magical thing is, it is counting some quantum gravity degrees of freedom, which are not the degrees of freedom we normally get from atoms or whatever makes a star. But we don't even know what is causing this entropy. We can't see all the states going to it. The black hole has nothing to see. All the stuff is in the central dot, is all empty. But still magically we know somehow what its entropy is. So it's all very interesting stuff, but just by pure logic of saving the second law of thermodynamics, we know the black hole has an entropy like this. But you can see at first this gives Bekenstein a minute of pause, because if you have entropy, the first law of thermodynamics tells you T ds is dE. E is just mc squared. The black hole has a mass, and the entropy now we know is the area. So if you do that, the black hole will have to have a non-zero temperature. And then if you go back to startling, if something has a non-zero temperature, and if it can absorb, then it must also radiate. So if the absorption probability is P, then the radiation at temperature T is given by P divided by e to the omega by kt minus 1. There's a standard relation like that. So if it absorbs but doesn't emit, in that case, you have a contradiction with detailed balance of thermodynamics. So actually, if you didn't know, black holes didn't emit, and everybody thought black holes can absorb everything, but because the structure of light holes we saw, at least classically, nothing can come out of the black hole. So at first it looks very puzzling. Black holes cannot emit. So if they have an entropy, they should have a temperature, and now we have a conflict with statistical mechanics. But of course, what Hawking had found was that if you take quantum mechanics into account, that light was going in is not the whole story. Quantum waves do a different thing, and they stretch, and then the vacuum becomes unstable, produces these pairs, and in the end, the black hole actually radiates with the temperature, and actually fits the scales we had for this temperature beautifully. And if you then just use TdS equals dE to compute the entropy, you get this factor I had on this slide. So now we know exactly the entropy of the black hole. So Hawking just computed the temperature, and from there you put in TdS equals dE, you get this. And that's quite remarkable. We can't see any of the states making the black hole, but we already know how many states there should be. And so that's a good marker of where we should aim to get our final theory of quantum gravity. If in your theory of quantum gravity, for a given mass m, you can find exactly this many states. You take the area of the horizon, divide by Planck square, whatever you do. If you get exactly that many states, that theory looks like we're on the right path. But if you don't get the states, theory is probably not correct, because it actually have a conflict with thermodynamics. There was a question for me? Yes.
Yeah, a nice question. If the number of states depend on, it counts the quantum degrees of freedom, then why the entropy should just be the spatial three-dimensional area?
Excellent question. Nobody knows the answer to that. Okay, so the whole magic is that this abstract argument of the saving second law told you that there should be some entropy to the black hole, but once you know the temperature, you don't check anything else. You just check the answer, and you find from the temperature this is what it works out to be. The temperature actually is 1 over 8 pi Gm. That's all I'm talking about. From m, you can try to write in terms of just m. You can leave it in terms of m. You can put in terms of Schwarzschild radius, which is 2 Gm, or you can write in terms of the area. The neatest way to write it is in terms of the area. That's why we wrote it like this. But why is it to do with the area? Excellent question, and we still don't know the answer. But the temperature is a calculation, and then from the temperature to here is 1 line. There you get the answer. Okay, so now everything is fitting together very beautifully, because we have the whole thermodynamics and we know the entropy of the black hole. But right the next year, Hawking noticed there was a serious problem with what he had found. And that's what the information paradox is. So now let's go there. So Hawking radiation came out by these vacuum fluctuations with net energy equal to 0. We call the outside number of this, let's call it B. I'll call the inside number of this pair C. But this was the picture we had. But now if you look at the vacuum fluctuations, they can either be with the electron inside and the positive outside, or they could be the other way around. And in general, you will actually get a superposition. So I wrote it like this. There's equal chance that this guy is inside or this guy is inside, going back to the kind of question you just asked. And what I actually get is a linear superposition. So when I do this near the black hole, the same thing happens. The state which I produce is actually an entangled state in the following way. The particle which comes out, that's an electron if the guy inside is a positron, and that's a positron if the guy inside is an electron. So if you ask me what is the guy outside, it doesn't have a definite answer. It's a conditional answer depending on what is inside. Nothing wrong with that, because in quantum mechanics, if you, for example, have two electrons with spins and you make the singlet state, in the singlet state it is up, down, minus, down, up. So this electron by itself doesn't have a state. It is up if the other guy is down, it is down if the other guy is up, but by itself it doesn't have a state. So this is standard quantum mechanics, and we know that. But we are now seeing that the same thing happens automatically when you have Hawking radiation. And then you see that the particle which is outside is quantum entangled with the particle which is inside, because they stay together. It makes sense, but by itself it doesn't make sense. We just schematically write that by saying that two possibilities, E plus or E minus charge, or sometimes it's just the spins. We can call the states 0 and 1. Any two states can be called 0. It's a standard language from quantum computation. So you can say that the state could be entangled like 0 for particle B and 0 for particle C, and then plus 1 for particle B and 1 for particle C. I just normalized it. So this is just a schematic way of writing what the entanglement is. The state doesn't have to be precisely this. But an entangled state is something which is not a wave function for B times a wave function for C. It is of the form of wave function of B times a wave function of C, plus some other wave function of B plus times some other wave function of C. And the number of terms that there are in the sum, that is how entangled the two guys are. So if there are, roughly speaking, two terms in the sum, both equal, we say the entanglement is log 2. If there are three terms in the sum, the entanglement is log 3. So we won't need that, but that's how entanglement is measured. How many terms there are in the sum? If there's only one term in the sum, it's a factorized state. The entanglement is just 0, and there is nothing to do about it. Okay, so now let's see what happens. So I wrote this thing here again. If you have two systems A and B, the total state will be something of A times some state of B, but then you're summing over many such things, and roughly the number of terms in the sum n, the entanglement will be log n. So anyway, the entanglement is growing, and after you emit n particles, the entanglement actually becomes n times log 2. So if you plot time versus the entanglement entropy, you find the entanglement is just steadily growing, and that's what's going on. And now you see the problem, because in the end, the black hole is going to go away. So we just had the vacuum and we had these guys left. And now you can ask, if that happens, what is the state of these guys over here? And now you find there is no answer to this question. Because if you had two electrons which were entangled, it doesn't matter how much you separate them, you can keep one here and one on Mars. This is up and that is down, plus down, up, minus down, or whatever you took. But if one of the electrons disappears from the universe and doesn't exist anymore, then there's no way you can define what the state of the other electron is, because it was up if the other guy was down, down if the other guy was up, but the other guy is not even there. So if you're left with only one electron out of the two entangled pairs, then this guy doesn't actually have any quantum state at all. Now that is very serious, because normally in quantum mechanics, you always have a state for something. And so now you can just see the entire information paradox in this one slide. You start with a star which had a well-defined state, some psi initial, very complicated, but some state of all the atoms in there. Then makes a black hole because it stops burning, then it creates these entangled pairs, and then in the end the black hole is gone. And these guys can't be described by any quantum state. And that doesn't agree with quantum mechanics, where if you have some initial state, there will be some Hamiltonian, would be pretty complicated, but always gives you a final state. But then this beautiful argument tells you that we don't actually need to know what quantum gravity is. Whatever quantum gravity is, it can't be described by the normal evolution theory of quantum mechanics. It won't work with any Hamiltonian. So in fact, Hawking came and said we should give up normal quantum mechanics and we should describe things not by states, but by density matrices, which don't have the full information of a state, because you will always make and evaporate black holes in a full theory of quantum gravity, and so you always lose the state property anyway. So we should start from scratch with no states. And everybody really hated that, because you love quantum mechanics. It works so beautifully everywhere else, but Hawking came back and told us in 1975 that if you have black holes, then you can't really have quantum mechanics. And the beautiful part is, it doesn't require anything to do with quantum gravity. Any quantum gravity would probably come only at a singularity where the curvature becomes Planck scale, But this argument only involves the horizon, but the curvature are actually very, very low. So the curvature at the horizon of a black hole of the size of the center of galaxies, 10 to the 8 solar masses, is the same order as the curvature in the silver. There's no funny quantum gravity going on here. So whatever you want to do with this process, nobody could find anything wrong with it. This pair production is the same as the one you get in the lamp shape, the vacuum fluctuations, the same as Schwinger pair production. Everybody understands this process, everybody understands the energy balance, and then you find you just don't have a quantum state. So that's the black hole information paradox. And the question is, how are we going to get out of it? So at first it looks like string theory shouldn't be able to do much either, because string theory just tells you what happens at the Planck scale. So at the Planck scale, when everything going to become singular, you have something which is stringy, there's something called string length, which is also of the order of Planck length. And anybody might agree that the dot in the center might not be a dot singularity, it could be smeared over a few Planck lengths. But as we just saw, that doesn't solve any problem. This is all to do with the horizon. So it's not clear if string theory can help you. And for a long while, string theorists weren't even thinking much about the problem. But let's begin with string theory and see what turns about black holes, and let's see where it takes us. Okay, so in string theory, you just have a known set of fundamental objects. You obviously have gravitons, because any theory of gravity has to have gravitons. But the other objects are not generically point-like particles. The special thing is they are more like elastic objects. They're like strings, or they could be high-dimensional sheets, and all these have the property that if you just let them be by itself, they shrink to zero size. But if you stretch them, the energy is just proportional to how much you stretch them. So that's all there is to know about string theory. So you have gravitons, you have strings, you can have five-dimensional sheets, they've got fibrates, and so on. And so you have these objects. And so if you ever want to think about a black hole in theory, you have to make a collection of such objects, put them together, make a bound state, that will produce a heavy mass, and then that's the black hole. There's no other way to make a black hole. So if you can study bound states of these objects, then you are studying black holes. Okay, string theory lives in 9 plus 1 dimensions, as you probably have all heard. And if you want to, let's say, talk about black holes in 3 plus 1 dimensions, so then 6 directions will have to be compact, so we can make them into compact circles. I've just schematically drawn one compact circle here, and then these are the objects. And so what can I do with them? I can take a graviton and let it run around the compact direction like this. The compact direction is really small, maybe a few Planck lengths. So if you are somebody who can't resolve the compact direction, like today we can't resolve a few Planck lengths, we just see this part of space, and this guy racing around just looks like a blob of energy to us, which is sitting at this position in the space. Similarly, if you take a string, you can wrap it around the compact direction, elastic band. If you can't resolve that direction, this looks like a point mass sitting here. You can wrap a 5 brain on the 5 circles, not in one circle, but like you have 6 directions. You can wrap a 5 brain there. It looks like a blob over here. But these guys don't just look like blobs carrying mass. They're actually also blobs carrying charge, because if you could have the graviton going this way, it looks like positive charge. If you let it race the other way, it has negative charge. A similar string also has orientation. You wrap it this way, you can wrap it that way. They also actually have charge. Anyway, that's a technicality. But now what we want to do is not look at these guys separately. We want to make a bound state. If I put them all together, okay, you can see I've made schematically drawn a bound state. There are 5 brains, there are strings, there's some gravitons attached to it. It just makes a heavy blob here, which carries all these possible kinds of charges, and there. That should be what I do to make a black hole. Okay. So now what can we do with this? Well, in string theory, it's a unified theory of gravity and matter. So there's just one coupling constant. So you could start with assuming the coupling constant is small or even zero, and then you have no gravity, and the interaction between the brains is also weak. So you can just go ahead and calculate anything you want. And so what do you calculate? You take a certain number of brains, maybe to make a heavy object, you need 1,000 of these brains, 1,000 of those brains, put them together, and you can count how many bound states do you have. So that's something you count in quantum mechanics all the time. If you have a proton electron, you count how many bound states for a given energy. You do this for the hydrogen atom in the mechanics course. It's the same calculation. If you take bound states of all these brains, you can ask how many bound states at a given energy. What is the degeneracy? And the answer works out. The number of bound states actually goes quite rapidly with the number of brains. So for the N1 brains of the first type, N2 of the second type, N3 of the third type, the answer that you get for the number is like this. So you know the entropy is the log of the number of states. So the entropy here is this thing sitting in the bracket. So you can see the entropy grows surprisingly fast. It's like N1 times N2 times N3. So it's actually growing surprisingly fast. But anyway, this is what it is. It's a weak coupling calculation. So actually there's no black hole here right now, because there's no gravity. There's no like metric or nothing produced, no zone of attraction. But now you can consider increasing the coupling constant to a large value, and then you assume that that mass will now generate some gravity. And for the same mass and same charge, you can write down the standard equation for a black hole with that much mass. So just go to your GR book and write down that equation. Yes.
in this weakly coupled theory, if there's no gravity, what is binding these into a bound state?
So they actually still have a binding. So for example, even at zero coupling, if you just take the string, and first let's ask if two strings bind to each other. And they do, because all very geometric. You take a string wrapping on a circle, that's one string. Second string wrapping on a circle, second string. The bound state is simply a string which wraps twice and joins to itself. It's a threshold bound state. If you want to bind momentum to it, what happens? The gravitons do it. You simply get a string carrying traveling waves. So those are the bound states. So even at zero coupling, all these things have a threshold bound states, and you can count it.
Should I understand them as real bound states in some limit where the binding energy is going to zero or something? I mean, exactly.
So if you have
and physically, what is the origin? I understand that you can make them in some way by these.
So you're asking why are they binding if there's no coupling?
Yeah.
Yeah. So
or is it that it's just very weak coupling, so they can bind but not very much? It must not be very tightly bound, right? In some sense, the binding energy is zero.
So right now it's threshold bound. Yeah, it's a threshold bound. Right? But if you change the moduli of the theory, for example, if you make the torus not exactly square, then momentum and winding are actually bound. Because the total energy, if you have n1 units of string and n2 units of the graviton, the total energy is square root of n1 square plus np square plus 2n1 np.
Yeah, I'm just asking what's the physical origin of this binding?
Okay, so it's very interesting. The simple origin of this is the same as the formula which gives you kinetic energy plus potential energy is special relativity. So if you take a particle of mass m and give it a kinetic velocity v, the total energy is square root of m square c4 plus the kinetic part, p square c square. And so because they are two pieces added together, separately they have more energy than together. And it's the same thing if you trace back, actually leads to the binding. It doesn't actually have to do with the coupling.
It's just sort of special relativity definition.
It is just special relativity. Yeah. So if you take like a string like this and you make it move relative to itself, it has extra some kinetic energy and some rest energy. But the total answer is a square root. You can't remove the energy from it. And so it's just a property of that binding. Okay, so if you go to strong coupling, now you think this guy will have a zone of attraction, like a black hole, you open a GR book, you put this much of charge and mass at one point, and you ask what will be the area of the black hole, and you compute the Bekenstein entropy for that guy. And magically, these people strongly and forward with this system, extending an earlier work of Sen from just a year ago. He had just taken two of these charges, not all three, he took two of them, but these guys took all three. And then it turns out that you find that the microscopic entropy from this counting is exactly equal to the answer you get from this one. Of course, you might say if you change the coupling from weak to strong, then has that perhaps altered the number of states? Should you really be comparing weak coupling to strong coupling? But fortunately, all these black holes are what are called supersymmetric black holes. That's because they also have charge along with having mass. And it turns out all the fundamental objects in string theory have charge equal to the mass. So what does that mean? If you take two guys of the same charge and mass like this, two identical copies of something, the gravity makes them attract, the electromagnetic force makes them repel. They're exactly balanced. You say Q is equal to M. All the fundamental objects in string theory have Q equals M. Okay, so they make what is called an extremal black hole, and those are also supersymmetric. And for them, we know the number of states don't actually change between weak and strong coupling. So everything is still good. And the important result is this: the microscopic count, if we could count only at weak coupling, because strong coupling we don't know what's happening with quantum gravity anyway. It magically matches this area quantity. So certainly you know that string theory is on the right track, because it has got exactly the right degrees of freedom, even all the factors of 2 and pi have fit. And just to compare most of the other theories of quantum gravity, the answer they find for the entropy is 0. And that's because of this theorem of Wheeler. Black holes have no head. If you try to write down a black hole, you try to see what you get. You just see this mass in the center, it's all vacuum outside, you get a unique structural solution, there's nothing to count. So nobody could find any entropy for the black hole. And even here, we haven't really seen the entropy. It's just that by comparing it to weak coupling, we found a way of counting. So we haven't really solved the problem, but at least we are right on the dot. And then if you compute the radiation rates from these guys, at weak coupling, you can compute a radiation rate from some bound state to radiate something just by its own excitations. You find that radiation rate exactly agrees with the radiation rate form. Okay, so it all seems to be going in the right direction, except everything has been done at weak coupling, and then compared to the black hole, which is a strong coupling. So you don't really understand black holes. And that's what I tried to write in this slide here. It shows you on the right track, but there are no states to count here, so you still don't know what you're counting. You're simply measuring the area. And you also don't know what happened with the emission, because In the gravity picture, you are having all this information paradox. We are actually the weak coupling emission from brains. There's no puzzle there. It's just normal emission from normal objects. So you can see all these troubles are coming because you have a vacuum around the horizon. This particle pair creation, it happened because there was a vacuum here, and then the vacuum became unstable and created the pairs. The same trouble is happening with the entropy. There's a vacuum here, there's nothing to count. If you had like a piece of coal or some other object, you look at the atom and see there can be different places, count all the possibilities, you get the entropy. But a black hole sucks everything in. If it sucks everything and you have the vacuum here, there's going to be nothing to count. It's the same thing if you get to this problem. If you have the vacuum here, it's unstable and you get these pairs in a piece of coal, you just can't do this. So something is wrong with this picture, but we've got to figure out what.
When you say vacuum here, you mean inside the horizon or outside?
Or straddling it in this region. Because the Hawking calculation used just this region around the horizon.
Near the horizon on both sides?
On both sides. Near the both sides. Okay, so just to compare, if you took normal bodies, like a piece of coal, how do they radiate? You could have an atom here, the atom emits a photon, that happens. So the atom and the photon can be entangled with each other because the atom might be spin zero. You can emit a photon with spin up and the atom will be left spin down. Or it can emit a photon with spin down, the atom will be left spin up. So they are also entangled. I've drawn the entanglement with this line between them. But after some time, this atom also drifts out to go out like ash. We want to evaporate the coal away completely. So by the time the coal goes away, you have photons and atoms, but they are entangled with each other, not with what is left behind. So the normal graph of the entanglement as a function of time for a piece of coal, in the beginning it does go up. You can see it was going up. But in the end, it comes down again. This is called the page curve. You've been hearing about that in some talks. It's called the page curve of a normal body. In the end, it should come to zero. There's vacuum there, the whole core has gone. You really can't entangle with that. But in the black hole, the problem is the particle that we create from the vacuum. And all the way to the end point of evaporation, the entanglement is just keeping on going up. And then at the end, you say, I don't know what to do because the black hole disappears and nothing to entangle with. And that was our paradox. Okay, so let's see what's the solution to the puzzle. String theory seems to be going in the right direction, but we still don't seem to understand what to do with the black hole, which are string theory as strong coupling. We can only understand them at weak coupling. Question.
Basically, I was wondering, like, if there is a charged black hole, see, when there are particles produced, there is a finite probability that the black hole is charged. So, what is meant when the black hole actually evaporates? Because the charge suddenly, forget about the other things. The charged black hole disappearing, like evaporating, would mean that suddenly the charge vanished.
Good. I think I understand the question. It doesn't happen.
The reason I'm asking is that because if there is something which is preserving the charge, then the entanglement is not really gone. Meaning with the rest of the.
Yeah. So a charged black hole will not evaporate. It will come down to extremality, where it is charge equal to mass, and then it stays there. Okay. So an extremal black hole which has charge equal to mass actually has zero temperature. It doesn't actually have any evaporation. But if you start with a black hole which has more mass than charge, it evaporates all the rest of the mass till the mass becomes equal to the charge, and then it stays there. Okay. So there is no contradiction with that. But the problem is if you start with a big black hole which was, let's say, neutral or close to neutral, you will emit so many particles that entanglement will be huge. If in the end you have charge of 2 or 3 units left, there can be 2 or 3 bits sitting in there. But those 2 or 3 bits have only like 2 to the 8 states of space. It cannot entangle with 1 million particles which have come out. So the number of particles which come out of the solar mass black hole is 10 to the power 120. So if you are left with 2, 3 bits at the end, it cannot really entangle with that. You need about 10 to the 120 states inside to entangle 10 to 120 states outside because they have to entangle like this, each with each. Okay, so let's see what the solution to this is. And so in string theory, we said the black holes are made like this by taking strings and pins, but we should now ask what is the structure of such a bound state, not at weak coupling where these people like Stromby and Bappa had already studied this, but we should ask for the structure of this bound state at strong coupling. So as we said, that's not such an easy question because when you go to strong coupling, gravity is strong, all the other couplings are strong, so how do you actually find the structure of the bound state? But it turns out it is possible to do that if you start with looking at very simple states and then moving to more complicated states. So that's what we really have to do, and that's what we are going to do. And so the typical idea people had at the back of their mind was, at weak coupling, if you make a bunch of strings and rings, what is the size of the bound state? So the only natural scale is Planck length. So maybe it will be like Planck scale, Planck length NP. And then if you go to strong coupling, then there will be gravitational field around it. The brains and all are quantum objects, so this will have a size like Planck length, but the radius of the zone of gravitational attraction, well, that of course will be very big, and that's the horizon radius, could be 3 kilometers for a solar mass object. So this was the picture the Stromberg Markov also used to match to at the strong coupling region. But then when you actually start looking at these bound states of rings and you increase the coupling, you find something funny. If you make an estimate of this size of the bound state, you find actually starts increasing as you increase the coupling. And somehow what the expression for the radius of the bound state, which is called d here, up to a factor of order 1, which we are not trying to fix in the estimate, it grows with the number of charges you put in here. It also goes with the string coupling. And then there are the other parameters here which tell you the size of the compact direction which are wrapped and so on. But there are 7 parameters here for the black hole I was describing. And the size of the bound state you get when you estimate the size of the bound state, which you this number d, magically all these parameters fall in exactly the right place to create a quantity which the radius of the black hole will that the short string. So that suggests something interesting, that perhaps in string theory, we are never actually able to compress anything inside its horizon size. The bound states automatically want to swell up as you increase the coupling, and they always remain a little bigger than the size of the horizon, in which case you never actually make a horizon. And then you have none of these puzzles because you never have a place where you can actually have net negative energy. You never have any Hawking pair creation, and the whole interior structure of the black hole is completely perfect. So this was just an estimate, so going back to 97, but it suggests the idea that all the states of black holes will be like this. And we have to now understand how did this happen. Because now we're going to see actual structure. We take particular examples and we can then one by one we can look at the states. This is only an estimate, but we can actually make the wave function of states one by one, and we find they're all going to have this structure. None of them have ever, all the states which have been made over the past 20 years, none of them have ever been found to have a horizon. So in string theory, it doesn't matter how hard we try, we can find a wave function of a lot of bound states which contribute to this entropy we were counting. In the simplest case of the Ashokan black hole, we can explicitly make all the wave functions of all the states, and none of them have a horizon. So the magical thing we need to understand is, the horizon was something very big, like 3 kilometers for a 3 kilometer black hole. And so how did it happen that the physics of quantum gravity, which we normally thought would only operate at the Planck scale and maybe make some changes on the Planck scale, how is it changing something all over such a macroscopic size? So maybe I can just make a comment on the answer to that, and then we can go to see what actually happens. The idea that Planck length is the only length scale that you can make out of C, h bar, and g is true. So if you collide two gravitons, new quantum gravity effects happen only when the wavelengths get down to Planck scale or smaller. Okay, that's just by dimensional grounds. But to make a big black hole, we are going to also take a large number of particles. Those are the numbers n's which are coming. And so now you have to ask, if you take a million particles, then the length scale of quantum gravity, is it Planck length or is it maybe a million Planck lengths? Now that depends on the theory. Like if you're in nuclear physics, the nuclei are doing hard sphere packing. So if you have atomic number A, the radius of the nucleus is A to the 1/3. If you're doing a Bose-Einstein condensate, all the particles sit on top of each other, size of the bound state does not grow with the number of particles. See, it depends on the theory. And what we are now finding is that in string theory, the size of the bound state grows in this particular way, so it's always of the order of the horizon size. Okay, what we really have to understand is what's actually going on in there. Let's look at the example of a few of these actual states and see what kind of structure they do inside, what's really going on in place of what we thought is the black hole. Okay, so we have these three kind of objects. If we join them together, we can make this. So we can write it like this. We have these are the brains. In that we put the strings. We can break up the strings and join them in various ways, like loop them around in various ways. We can partition the gravitons moving on them in various ways. So we can just make diagrams like this. These indicate spin degrees of freedom. Just a schematic way of saying the bound states are very complicated. Okay, but each schematic picture like this tells you one kind of bound state you can make, and then there are all these bound states that come. The one that Ashok Sen studied had only two kinds of objects. You can take 5 brains and strings, but leave out these blue things. That's more like the Ashok Sen thing. So first we looked at this thing which only has 2 guys in it. It's also a tiny black hole. And in this you can make all the states. If you write the normal metric that you find for this kind of black hole, it has mass plus charge. The metric looks like flat space far away. As you come close, it develops like a throat, which is true for charged black holes. They have like a narrow throat like this. And then in the end, you find a horizon, and this is the picture you would use. It doesn't really actually make the wave functions correspond to all these states. By the time you never actually reach the horizon, at some point you come, and the metric just becomes some messy object, but actually doesn't make a horizon. So we actually got the explicit wave functions for these guys from all the possible states, and you can go and see that none of them make a horizon. But if you see the size of the region where this messy object is happening, and then the boundary area of that, and divide by g, you get the order of the entropy. So they're having the right kind of size that you get for the Bekenstein formula, but inside is not empty space with all the mass in the center and the horizon. In fact, there's no horizon. It's just something smeared all over this region.
So how do you define the fact of not having a horizon? Classically, one would analyze
That's exactly what you do. So you take the explicit metric and see from every point there's a time like a path or null path which can come out. Exactly. You look at exactly that. That's the meaning of a horizon, but there's no horizon.
Because Samir, could there be a simple physical argument that such as this fuzzball system is not divided to horizon?
Yeah, so
what prevents the formation of?
So let's make a very, okay, let me give a very rough argument for the sake of it. What is roughly happening is that in the theory of normal particle physics, you only have point-like particles. And so you put a lot of energy in some region. All you can do is make the particles move faster. But then they just follow normal love calls and they go to the center in the usual way that everybody was thinking. But in a theory with objects which can stretch, if you put a lot of energy in something, the energy can go into moving them faster, but it can also go into stretching them. In fact, there's much more entropy to stretch the net, because there are many more shapes to it. So what is happening is if you make bound states of many guys which can all stretch, then the phase space all goes to the part where the objects actually want to stretch. And the more energy you dump into it, the more they want to stretch. And so that's where the states are. The states are all where the objects have stretched and stretched with that much more energy you put, they stretch all the more. And then they actually start moving like this mess.
So then you have some kind of analog of your the exclusion principle for this, that to put more the thing, then things get more and more stressed, so you cannot confine.
So you can actually see it very explicitly, because maybe later I could show you how you make these metrics. And in this case, it is very simple. You just have a string which is doing certain kinds of oscillations. You simply have to find the metric of a string carrying certain kinds of vibrations. The metric of a string is known in string theory. The metric of string carrying vibration is also known in string theory. You simply have to write it down. It turned out nobody had actually written it down, because it can have various variation profiles. All the different ways of vibrating it are all the different entropy states. You simply have to compute the metric of a string which is vibrating, but at strong coupling, not perturbating. But that is absolutely doable. So in string theory, there are techniques to do that. So the moment you do that, you have the metric you want. And then every different vibration profile of the string is a different microstate counting towards the entropy, and has a different metric. And that's all this is. Maybe we can go to that. Right? Okay, so then there are many states of this which have been made. Let me just skip over this in the interest of time. Let's just take a brief look to see what actually happened. What is how would a gravity person understand that we completely change the inside of the black hole? What did we get instead? So let's look at a cartoon diagram to understand that. This was our picture of the black hole from before. This is the heavy mass, and in here you should get negative energy. We said all those things. Before instead of drawing all this, let me just draw one space direction x for simplicity. That's my x. I won't draw the other ones, but then my mass is in the middle. This is the horizon radius 2g by c square. I just plot it down here from here to here, and here's the place of negative energy. I just reduce one dimension for simplicity. But now suppose there was an extra compact dimension in the theory, so there is my compact dimension. There are 6 of them. I just draw one. So now my space, instead of being a line, it's like a drinking straw. And at first, of course, people had no compact dimension ideas from a long time ago, 1980 onwards, but it never seemed to do much, because this was maybe a few blank lengths. We're talking of kilometers on the horizon scale over here, so the extra dimension just seemed to go for a ride. You just let it go everywhere. You still have the central mass here, horizon radius here, negative energy location here doesn't seem to have made any difference, except now you have a completely new topology possible. You take this entire region inside the horizon radius, you cut out that part of the drinking straw, and you throw it out. And then you might think you got a cut, like if you come here, where will you go? Will you fall off into nothing? But no, you close up the end of the straw, like smoothly like a cigar. So I've done that. Now this is a new topology. And now you see, if an ant is crawling here, you just go back here, there's no way to go inside the horizon. In fact, all the area which is inside the horizon is gone. You could ask, where's the mass which made the black hole? That used to sit here. But that energy is in this curvature of these places. So what is very interesting is that when you actually start take some strings at weak coupling, you can find the metric they produce at all couplings. You can just write down the answer completely for all couplings for this thing with 2 charges. If you ask what kind of metric they produce, if not the black hole metric we had on the previous slide, which looked like this, it doesn't actually look like this. It doesn't look like this. In place of that, as you follow it through string theory, it actually gives you this. So that's the structure which you get, and if you go to 3 dimensions, that's the way you should see it. If I want to make this in 3 dimensions, imagine from the middle of the room, I cut out a ball and I throw it away. That's not part of space-time. Everywhere there's a compact circle that lives everywhere. As I approach the surface of this hole which I cut out, it comes and closes off like a cigar. There's a twist to the cigar left or right, that's a technical thing, but I've known that the plus or minus, different ways of doing that actually account for all the different entropy states, modern speaking. And this structure is what we call the fuzzball. All the states which you get, which anybody has found for the black hole so far, they all have this structure. But you can see none of them have a horizon. None of them have a place where you can get net negative energy. There's no normal Hawking radiation. All that is gone. So in string theory, we've been doing this for 20 years and nobody's been able to make any state with a horizon. So it looks logical that all the states will be like this, and then you don't actually have a puzzle. Let me skip all the technicalities, but many, many different cases of putting the brains together in many different ways to make different microstates have been solved, and so we have a lot of solutions like this. Okay. So it looks like you can basically see there are all special cases because there's something a lot of symmetry you can make it. There are lots of things in the middle here which are very complicated, which nobody has yet tried to make because technically it's a bit more difficult to make them. And so somebody could always ask, could be the states you haven't yet made, could be that those have normal horizons? It looks a little strange to ask that, but you could. How do you answer that question? Well, first you would ask, why would anybody ask that? If you've taken all kinds of special limits and all the 2-charge states you've made, many of the states with 3 charges you've made, and they don't have horizons, why would somebody go back to thinking that the ones which you haven't yet made, maybe those do have horizons, and the ones you've done are only special cases? And the reason was because people had a mistaken belief in something called small connections. So what was the idea? We had this entanglement story. This guy is entangled with this guy is entangled with this, and so on. That was Hawking's leading order calculation. But there could be some small connections to that calculation. And so there could be extra entanglement between guys which we haven't thought about, all the other guys which are drawn by dashed lines. So they would be very small. If they're very small, then why think about them? But the number of particles emitted from the black hole is very large. Mass of the black hole is 9 units squared. That's a big number. So if you have small corrections from some quantum gravity source, but there are many of them, maybe that completely changes your answer about the entanglement. And maybe there is no problem. Maybe the entanglement actually comes down. So perhaps if you take all the delicate ones into account, the entanglement will come down. In 2004, the bet that Naresh was just talking about was actually a bet taken by these 2 people with John Preskill. The Preskill was saying, I don't know how it will happen, but somehow the information will come out in the black hole immediately. And these guys had said, no, I don't think it will come out. But based on this argument of small correction, which was actually put out by Maldacena in 2000, then Hawking reinterpreted that as some language saying there could be some leading saddle points, but that basically means in the Hawking theory you will get some small corrections. And then he said the small correction probably overwhelmed the leading order answer he had himself found in 1975. And so he surrendered his bet upon just his encyclopedias. But Kip Thorne didn't pay up. He said, look, I haven't seen anything that you could do with the small corrections. I don't see how they're going to fix any problem. A small correction should make a small effect. Doesn't matter there's so many particles, I'm not giving up. So the question, who's right? Was this guy right or was this guy right? It turns out you can actually prove something called a small correction theorem. This was the state that Hawking used. Suppose we make a small correction to it, which is of order epsilon. The number of particles is huge, but you find the entanglement actually keeps monotonically going down. So if you make a small correction, you can reduce it, but if epsilon is, let's say, 0.01, you reduce it only by 0.01. So actually, in this case, Hawking was wrong to surrender. This is not the reason that the whole thing works. This is what you have to use some the quantum entanglement entropy, but with that you can prove that whatever Maldacena was thinking and Hawking was picking up on was actually not correct. So what does that mean? It means that you can't actually keep. Just write this on this slide over here. If any of these guys in the middle, which we haven't made, if even one of them actually has a horizon to leading order, it will have small corrections around it. But if the horizon for even one black hole looks like this room, like everybody thought, it's like normal empty space, you can have small quantum gravity fluctuation, always possible. But if it looks like that to leading order, you cannot save the information. So that's very important because now we know Hawking's argument can be made into a rigorous theorem. You have to make an order one correction at the horizon. And that's what the fuzzballs are giving you. We've completely blotted out the horizon, all these methods. So people are very worried this is too big a change. But you can't get away from it. You need a big change. And all the metrics we're actually making, they have this big change. So I'm basically out of time. So I'll just talk about one thing and then just stop in a couple of minutes. This is what we really have to ask. How did the classical picture break down? The black hole is so big, it's a macroscopic object, 3 kilometers or even bigger. How did it actually change by quantum gravity effects with 3 kilometers? Why did the effect actually pop out to this large scale? And what happens is if you have a star and you try to see its gravitational collapse, it smoothly goes to the horizon, then the light goes turn inwards. We have seen that, you get a pair production. It all looks classical. So how will we have a change on this? But the point is, if you look at these fuzzball metrics we make, and take this collapsing star, you find there's an amplitude tunnel from here to here. Now the tunneling amplitude is very small because you can take a macroscopic object and it's tunneling to something else is obviously going to be very, very suppressed. But the beautiful thing is there are many, many states that you can actually tunnel to because the Bekenstein entropy we said is a very, very large number. So you have to multiply the small tunneling probability by the large number of states that you can tunnel with, and you find that this smallness is actually cancelled by this largeness. It's just a one-page calculation which I won't go through right now, but you can see that the Bekenstein entropy grows at a rate which is exactly cancelling the suppression of the tunneling. So that's why the black hole is not really a classical object. There are so many states in there that when you try to write the path integral, let's say for a black hole, normally we extremize the classical action to get the leading order answer, and we forget about the path integral measure, which roughly counts how many states there are. But if there are too many states in the system, then the path integral measure is huge. And what you have to extremize is not just the classical action, but also you have to add to it the measure and then extremize. And it completely tells you the classical action over and is compensated by the measure, and the whole object is not classical at all. So now there are many explicit things you can do with it, but that seems to be roughly how this guy is getting away from the classical. Let me skip this part about this and just come to the conclusion. So we already said this important thing that the Planck length is very small, and people thought physics should only change over the Planck length. But if you have many particles involved in making a big black hole, the quantum gravity effects could grow with the power of n, so then they could become macroscopic. This only tells you that it could. If you go back in detail to see why it happens, it's because the entropy is so big that there's a tunneling and the tunneling just invalidates the classical solution. There are so many states there that you just end up disappearing into one of those states rather than actually following the classical path. So at the end, I'll just say one thing, that today we are also getting very interesting puzzles in cosmology. In cosmology, we find something called the cosmological horizon. But that's just the time reverse of the black hole horizon. In the black hole horizon, light codes force you to go purely inwards. In the cosmological horizon, light codes force you to go purely outwards. Okay, that's just because of the expansion. And even the length scales and energy scales involved are the same. Whatever energy is required to create a horizon in this region, if you go to cosmology, the amount of mass in here is enough to make a black hole with radius equal to this value. So it's exactly the time reverse. Okay, so if we have found that in black hole physics, the entire interior of the horizon is actually altered by some quantum gravity effects, and that's how we solve the puzzle, then perhaps we should have interesting implications of this in cosmology, where we have all these puzzles which I just mentioned. We have trouble with the cosmological constant. We don't understand the energy required to drive inflation very well. These days we have something called the Hubble tension. And it turns out that applying these fuzzball paradigm methods to cosmology, we are finding interesting implications for each of these three questions. It seems there's an extra source of energy you can get, which might help us to understand these three puzzles, which are actually all happening at the same scale that the black hole has difficulties, at the same scale we are having difficulties in cosmology, and so solving one problem will actually help us impact the other problems. I'll stop here. Thank you.
Yeah. Yes. Actually, okay. Yeah. I was just wondering, like in the astrophysical situation, suppose the black hole, the horizon is ever forming, actually it does not form. Will the information, the loss paradox still exist? Meaning in the sense that suppose it's collapsing, but then almost in a distant frame, it almost freezes, like we actually don't see the horizon. But I don't know how the calculations were done, in which the time was used for the calculation. Suppose you write Schrodinger equation or whatever in the frame where the particle is freely falling. There the particle not even see the horizon. So, in a normal situation, like astrophysical situation, where the paradox still exists.
Yeah, so that's the part of the slide which I skipped because I ran out of time. So this is a question which everybody has asked. How does information come out of the black hole? In the Schwarzschild frame, it appears nothing goes inside the black hole, everything appears to freeze at the horizon. If you change to a Kruskal frame, it appears the object can just go in. And so you can ask, is the stuff inside? If it is inside, how does it ever come out? And that's always been the puzzle, right? The two patches, the Schwarzschild patch and the Kruskal patch. But now we do understand that. And the answer seems to be something like this. These are the couple of slides I skipped. I can just show you that to answer your question. Here's the shell which is coming in. If it passes this horizon, it's going to make a black hole. And suppose inside is somebody sitting drinking a cup of coffee. The question is, when does that person feel something? How does he feel it? And when will the information come out? These were the basic questions. Whatever you ask can be recast in this language one way or the other. And so you can see in the classical picture that the shell goes inside the horizon, then the light cones turn inwards, and now nothing will come out, and that's usually the puzzle. So this just states the puzzle. What actually happens? To understand it, you have to just look at something as a toy model, alpha decay. So in alpha decay, you have a particle bouncing back and forth in a well. You can look at that as a clock, ticking of a clock. So you can think of like any object, like a person or a clock, just some living object for the moment. But also has some object tunnel out, and then it goes up. So what happens over time? The clock is over here, but if you actually see, there's some wave function probability for the clock to be here. As time progresses, the clock period doesn't change. The clock is the same, but the probability of the clock existing goes to 0, and the probability of this thing going outside increases. So the clock sort of basically fades away, but its period doesn't change. The clock doesn't get demolished, its period doesn't change, but its probability just goes away. It's just standard tunneling. And now see what happens for the black hole. So as the shell comes closer and closer to the Schwarzschild radius, it starts tunneling into the fuzzball outside. We mentioned tunneling. You get tunneling into the fuzzball structure outside. So more and more of the amplitude here actually ends up here. So this guy starts fading out in the same way. So what happens is you need to actually describe two parts of the wave function, just like you need to do in alpha decay. There are two parts of the wave function. Some part of the wave function is here, and some part of the wave function is here. If you thought there was only one wave function, you get confused. Do I describe it here or there? But the two coordinates, the Schwarzschild coordinate keeping track of the outside, and the Kruskal coordinate keeping track of the inside, are actually describing two different parts of the wave. And that's what gets into the form. If you have two parts of the wave function like this, you should not try to join them into one Penrose diagram. That's where the mistake was. When you have a tunneling process, you're going to get two branches. It's like a Schrodinger cat kind of thing, right? You can have something with one branch where the cat is alive, one branch where it is dead. They each have their own natural evolutions. But if you try to put them together into one picture, it doesn't make sense because the wave function is split. So what is happening here is that because the large entropy of this black hole, the thing becomes very quantum even though it's very heavy. It's like a Schrodinger cat, which is, you have no difficulty imagining two electrons can be superposed, but we have difficulty imagining a cat can be superposed. But in principle, that is possible. Here, the large entropy is actually making that happen. And when you have two branches to the wave function, you need the Kruskal code to study what's happening inside, and you need the Schwarzschild coordinates to the part which is outside. So you really have to look at the full wave function and then see what you want to write in the Penrose diagram. And the Penrose diagram by itself as one diagram doesn't make sense.
You say a bit more about why information paradox are added to the Hubble dimension.
Yeah, so that is interesting. What we found was that whenever the cosmology enters a phase, so there are two horizons in cosmology. One is the particle horizon, which tells you how far light has gone, and the other is the cosmological horizon, which tells you where the light cones point outwards. They are roughly of the same order, but the actual ratio between them is a number of order 1, but depends on the expansion parameter t to the alpha. So it turns out whenever this alpha changes from the value of alpha equal to a half for radiation to alpha equals something bigger than half, like 2/3 for dust, at that time, you get an extra energy induced from the dynamics of this particular fuzzballs, which is of the order of the closure density at that epoch. So it turns out that in the Hubble tension, you can resolve the problem if you have this early dark energy, EDE as they call it, which is of the order of 10% of closure density at a time t star, which is the time of matter radiation equality. That's one of the resolutions of the Hubble tension. But when we were actually trying to put this kind of thermodynamics in there, we find that that's the time when the particle horizon crosses over the cosmological horizon. And then these fuzzballs actually give us an extra effect at that time, which is of order of fraction of the closure density. So we don't know if any of that is correct because we don't have that much control over it as we have over black hole. There you can take a state and just beat it to then write the full answer out. There we can only look at estimates and orders. But because it's the right order at the right time, we found that interesting. So that's the sense in which we've been playing with cosmology. We're just seeing what kind of effects we get at the cosmic horizon, different epochs. And the whole point is whenever the particle horizon crosses over the event horizon, the cosmological horizon, and that happens when the power law changes from a smaller value to a bigger value. That's the time this extra energy gets released. And that's somehow impacting all the three balls of generation.
Any other question? Yeah.
So, as per the fuzzball hypothesis, a black hole, what we see as a black hole, like the one at the center of the supermassive black hole in our galaxy, it's really a condensate of some string excitations, which happens to have entropy proportional to the area of that condensate.
Yes.
Right?
Yes.
So, why is it? I mean, do we understand why it should be proportional to the area and not something else?
No, I think there is no very clear answer to that yet that I know. We just observe that, for example, in the two-charge geometry, you can break them all and you can just see it's the area. But there are a little bit more things we can do because we have tried to study this issue. Ultimately, the size you are getting is coming basically because of black holes are optimally phase-space packed. So you know that you can't put more than one state in a cell D3x, D3p of volume HQ. So what is really happening with the size we are getting to these fuzzballs is because you've already packed the states as densely as possible, that's giving this particular answer. And then you can study that more delicately. You can look at a subset of the states, which are smaller. But again, you find you can never put more states in something that is given by the area of that. But why is it the area is not somehow, even though you can see it in front of you, we can't see why it's coming out to be the area. Okay. But there are other things we can prove that anything which is sufficiently close to horizon radius must have automatically the entropy, temperature, and radiation rates of a black hole. That's something we just proved last year. So there are many indirect ways you can see that you must have that answer. But very directly to see why is it the area, is there something actually standing at the surface of that area to account for it, we don't have an understanding. And it would be very nice to have that answer.
But it's expected that it would have to do with the extended nature of these objects, right? These are strings or grains, whatever.
True, but if you look at the actual wave functions, the wave function in the two-charge case where all the wave functions are explicitly in front of you, they fill the entire ball. There's not like they're hanging only at the surface. They fill the entire region, right? And yet, because there's so many things going on, the dilaton is going to zero, some metric is changing in certain ways and all that. In the end, when you multiply all the factors, the answer comes out to be the area.
So it looks like a conspiracy.
It looks like a conspiracy. So if we could read into that conspiracy and see why it is happening, it would be wonderful. But it also works for the black ring and all. Every case it's working, but we don't understand it.
Why not volume versus area?
Yeah, that's the question. Why is it the volume versus area?
Why would whether the null character of the black hole boundary has to do something? The black hole boundary provides.
So it's in some sense, yes. Yeah.
And so in one sense, you see anything that you have a one parameter less.
Okay, so this last paper I was just mentioning here, it sort of says that once something has a redshift bigger than something, if the surface such that redshift is larger than a certain value, then it must have the entropy and temperature and radiation rates of a black hole. That's the paper we did here this year. So that you can prove. So in some sense, the high redshift is the null condition that you're talking about. But that just tells you why it's the same as the black hole. Why it's the same as the area is not so clear to me.
Yeah, when you try to get the interior of the black hole or more any complex object.
Yeah.
It turns out that where I was suggesting that matter is only the kinetic matter, that is only the free particles which are moving and are only interacting together. They have to get this complex the bound 4 by 9. it turns out that these particles have to be confined to the inside.
Okay.
And so, in one sense, when you for the black hole, then it will be really the photons will be. So that's things, the cell thickness will tend to be only going to be.
So let's talk about it in detail because it's not like I understood everything, but I would like to maybe hear more. So let's talk about it offline. Yeah. Yeah.
So, if I understood correctly, you are saying there is an information paradox. The way you are solving it, saying there is an information paradox in string theory because there is no event horizon for the black hole.
That's exactly the answer. Yeah.
Right.
But also one more thing I said that a lot of confusion which the string theory people had earlier, which the GR people actually didn't have, is that you can't solve the problem if somebody said that they can keep the horizon and make any four corrections, which could be non-local. Suppose some magical thing which goes from the singularity A causally to near the horizon and makes a 1% correction to the dynamics. People were sort of hoping that some little subleading things which we haven't really understood somehow could induce delicate correlations between all the large number of particles going out and somehow solve the puzzle.
Okay.
So the theorem which I use, the small correction theorem, tells you that that is not possible. So that's also important because that makes Hawking's argument into a completely rigorous thing that you need an order one change there. So it's not like that string theory, of course, does that, but any theory which doesn't alter the horizon also actually cannot solve the puzzle is then also established by this small correction.
Okay.
So these both things together end up solving the puzzle because when you actually make the solutions, you can only make some of them. You can't make every state of every black hole. Just like you can't make all the states of even the Earth, right? There's so many states of the Earth. So you can make special cases and see they won't have horizons. But then to prove that nobody can have a horizon, you actually go to the small correction theorem and say, if even one state has a horizon, small corrections can't help you. It will actually always lead to information loss. And then together these two things seem uncovered.
Okay, so then I have a very naive question. So then this is resolved in like something around 15 years ago, right? Even the small correction issue. So why are people still working on black hole information paradox?
I think people have a lot of confusions, which is a sociological question. But I think largely I have understood one thing, that the people who came from to string theory came from the particle physics side. And the people who came from GR, they were doing quantum fields in curved space. And string theorists just don't have a good feeling for quantum fields of curved space. So if you talk to any young person today in string theory, they haven't worked through Hawking's paper.
Okay.
Nobody can reproduce Hawking's paper if he's under 45 pages.
One more question.
Sorry, just a general question, maybe a follow-up to the discussion. Samir. So Wheeler had this nice thought experiment. He said that why is the black hole really black? So I imagine somebody falling into the black hole and shooting out discrete packets of light. If he does that and time that he goes across the horizon, there will be a last packet at the center.
Yes, yes.
So in that sense, the black hole is truly black and the frozen star picture.
That's right.
What happens in the
Yeah, so the fuzzball is going to be approximately very black, but not infinitely black, because the fuzzball surface is a few Plancks outside the horizon radius. It turns out if you want to get any information out of there, it's very difficult. Suppose I draw the horizon surface here, and you're sitting, let's say, a distance delta outside the horizon. Then if you shoot rays at random angles, only the rays which are in a solid angle, which is delta over Rs, short radius whole square, will come out. All the other ones will just go in. So if you take the solar mass black hole and you have one Planck length outside, the solid angle which comes out is confined to the radial direction within a solid angle of 10 to the power minus 77. So nothing can get out, right? So that's basically the...
So replacing this discreteness argument with the probabilistic argument.
Yeah, so the redshift is very high but not infinite. So the redshift infinity have a horizon. Now redshift is very high because you can get to Planck length from the horizon, but it's not infinite. So it's very black, but not infinitely black. That's fine enough because you just want to read information from it slowly. So the normal is not cool, not just like any other star. It radiates from the surface and does the normal things.
Okay, yes. Last question.
Maybe like since you have now under the fuzzball picture, so you should look for black holes astrophysically.
So as I was just saying, if the fuzzball structure is confined to within a few Planck lengths of the horizon, it's not easy to see it.
So the prediction,
So I think that's why I'm actually focusing a lot on understanding cosmology, because in cosmology you are inside the horizon in some sense, right? So a lot of the models we are making for the dynamics of fuzzballs, a lot of that is guided by what we are seeing in cosmology. Because someday I keep cook up some model, the fuzzballs do this. But then I go and see in the sky, that's not happening. I just kick out the model. So by looking at cosmology, because just the time reverse of the black hole, I think we're going to get a lot of more data from this. If we can actually fit the Hubble tension or the cosmological constant, I think that's the best chance of understanding this. But all the gravity wave stuff and so on, that comes from the last stable orbit. That's inside. You're not going to see anything with just 2m plus black.
So let's thanks. So